What's up? Welcome to the channel. So today we're going to be talking about linear and nonlinear regressions using for the Antoine equation using sample data from water, pressure, vapor. And so let me go back to here. So first off, I'm going to import the source location of a CSV file that contains temperature data as well as the vapor pressure data for the water. So I'm going to import that in. And also, I'm using a website called Colaboratory run by Google, and it's free to use, and it can run code, and it outsources to an external server so that you don't have to use your device's GPU or CPU to run the calculations. So it's very handy and very nice. So I ran this, press Shift Enter to run this line of code right here. It's imported this. So if we go to files, we can see I have, well, this is from an earlier run, but I have a water pressure vapor CSV file in here. So let me get rid of that. And then if I actually go down to a new code, let me see if I can't. Okay, well, we'll just go down here. So next I have to import a numerical Python so that I can actually read in the CSV file. So I'm going to do import numerical Python, and then I'm just going to import it as NP just for later use so that I don't have to type in numerical Python every single time. I can just use the shorthand of NP. So push Shift Enter again, do that. So now I can say data equals numpy dot load text, and then I'm going to want to load this file name right here. So water vapor pressure dot CSV, and then I guess it imported as 2. So I'll be using that. And then also with the CSV file, if we look at it, pull this over here, you can see that it's since it's a CSV file, it's a comma separated values file. So they're all separated by a comma. So these are the temperatures in this list right here, and these are the vapor pressures. So if we go ahead, we have to set a delimiter equal to a comma, and basically all that's doing is it's letting it know that the values are separated by a comma. So when it's reading in the text file, it doesn't mess anything up. So press Shift Enter. Oh, did not put a comma right there. That is important. Or I guess I did not. Oh. Also, spelling is very important as well. So Shift Enter again. So now if I load in data and just Shift Enter that, now we can say we have an array. So these are all the temperatures right here, and these are all of the vapor pressures. Now if I pull up my iPad and we can explain things a little bit more. There we go. So essentially what we're going to be doing, so if we have a graph like this, temperatures are down here and the vapor pressure will be up here. And all of that is we're going to be plotting the vapor pressures, but we're not just going to be plotting the vapor pressures. We want to actually plot the log base 10 of those vapor pressures. And then eventually we're going to be drawing a line, which Antoine's equation should fit. The definition of it is it follows the line of the vapor pressures at different temperatures. So the Antoine's equation is actually A minus B over the temperatures plus C. So what we're going to be doing is we're going to be finding a line of best fit essentially. But what we want to do is for the regression is we want to find the best fit model, we have to take each of these data points and we want to find the difference between the values and Antoine's equation essentially. And now how we do that is using a sum squared equation, which it has to be. So we're going to move this log over to this side and set it equal to 0 essentially, and just get rid of that. So it's going to be the sum of the log minus a minus b over t plus c. And then, but since we care equally about whether one of those is above or below, we can't have negative and positive numbers in that, because it's just going to mess up all of this data right here, and it's going to equal into a 0, hopefully. And so we're going to actually want to square this whole thing before we sum it up. So if we go back to our code, let me stop mirroring. So if you go back to our code, we're going to, wrong window. So let me just get rid of this real quick. Now we want to access the temperatures and the vapor pressures separately. So what we can actually do is, so if we just want the temps, we can set that equal to data, put a square bracket, and we want all of the columns, or we want all of the rows in the first column. So we're going to put a 0 because Python indexing starts at 0. So then if we press Shift Enter, then if we press T, we can say we can see we have an array of all of the temperature values in one array. So now we can do that separately again for the if we want to take the log of the data. So we'll just name it, I'll make it lowercase, log p. We can say we want to take the log of it. So this is where numerical Python comes in handy, because now we can take the log base 10 of the data, all of the rows. So again, colon represents all of the rows in the 2D array, and then we want the second column. So with Python indexing, that becomes a 1. So press Shift Enter, and now we should have all of the log base 10s of the vapor pressures in this variable right here. So now what we're going to want to do is, so if we actually plot that, so let's go back up here to where I imported numerical Python. Let's also, so from Plotly, which is a the plotting service in Python, not numerical Python. So from Plotly dot subplots, because we want to access just the subplots, we want to import the function or the command make subplot. Subplot, and then I also want to just import that in as plot, just because I'm not going to be using anything else but that, so I don't have to type make subplot every single time. So Shift Enter that again. Something went wrong. Let's go ahead and retype this. I probably didn't import it right. So from Plotly dot subplots. I said subplot. So import make subplots as plot. So Shift Enter that again, and there we go, it works. So now with this, so we can do plot, and then I want, so right now we're using the subplot command for if you want to have multiple plots, but since we're just using one, so I want only one row of plots with only one column of plots, so just essentially one plot. That's all I want for that, and then there we go. Actually, let me get rid of that. I don't want it to plot immediately, so I want to say, we'll say figure equals plot, and then rows equals 1, columns equals 1, and then do that again, and then now it should just have figure. So now I can do figure dot add scatter to add a scatter plot to that figure, and then now from that I can set the x-axis equal to our temperatures, and then the y-axis, for now we're going to set it equal to the log p of our data, and then I'm going to set the mode of it, which is just saying what it is, to markers because I don't want, because it defaults to a line and I just want them as points because it's our true data points. So now if I press Shift Enter, these should be all of our vapor, the log of all of our vapor pressures for here. You can see there's a little gap right here, but that's just from the data, and as well as up here too. So now what we're going to do is we're going to want to transform this as shown on the iPad to a sum squared equation. So the way we're going to do that is we're going to define a new function, and I'm just going to call it sigma, and then we want to pass in one variable. We can just call that q, and then put a colon. So then now we need three variables because we're missing the a, b, and c portion of Antoine's equation. So we'll do a, b, c equals that q. Oh, not quit. Equals that q. And then from there, we can return actually, because we have to make sure you press return or else it's going to mess up later on down the line when it tries to call back to this sigma function. Anyways, but so we're going to want to return the equation that we want to have. And so for that, we are going to do numerical Python dot, because we want the sum of all of the logs, log base p, minus our a value minus our b value divided by our temperatures plus the c value. So now that should work. Oh no, we also need to square it. That's a very, very important part too. So we want to make sure that all of it's in there. So I'm going to put another parentheses. I am going to square that. And then I'm going to close that off with another parentheses and just make sure they all line up. So that one closes off that one closes off, that one closes off. Okay. So now if we press Shift Enter, I should now have a new function in my Python directory called Sigma, and it just runs this right here. So now what I want to do is I want to run this from the data that I have, and yeah, so if I go ahead, I can do, oh no, well actually, because if we plot this right now, it's not gonna, because the whole linear regression, we want to find essentially going through a bunch of calculus, we need to minimize this function right here. So we need to actually import another thing. So from scientific Python, so SciPy, from SciPy Optimize, which is a calculus written code, which saves a lot of time, so we don't have to do it all within this function ourselves. So from scipy.optimize, we want to import the minimize command. Oh, minimize. Okay, so Shift Enter that again. So now we have that in our directory as well. So now, if we can say, we'll just run it for now. So we want to say like our results are equal to the minimize of this function sigma, and then the variables that we want to pass in, we don't know the variables, but it wants you to give just general guesses, but we have no idea, so I'll just put in 0, a float 0, another float 0, and another float 0. So 3 0 floats, and hopefully it could give a good guess of what it is. So now we do that, and then now if we type in results, Shift Enter, that's why I was confused. I just pressed Enter. So it gives us all of these, so like a whole function number, an array of a bunch of variables and everything like that. It says the optimization terminated successfully, so that means it worked. It was able to figure out a equation for a line to pass through that this plot up here to fit this data as best as it can, and these are the variables that it got from the equation that we passed in, the sigma equation. So now what we can do is we can actually plot these numbers onto that with a little bit of extra code. But for right now, if we just said, hey, plot like results, it wouldn't know which number to get. We just want these x variables right here. So now if we get rid of this and we can say, we can completely unpack. So the good thing with Python is you can assign 3 variables at a time, or you can assign multiple variables at a time. So we'll just go our A nonlinear regression, our B nonlinear, and our C nonlinear is equal to results, because we have that function up here. We have this variable up here, and then dot x. So it's calling these, and since this is a list of 3 and this is a list of 3, the variable type should match up, and we should now have all 3 of these as those variables. So now if we go, we can do plot dot add plot dot add scatter if that is my fault. I allocated it as figure, not so figure dot add scatter. So I'll take in scatter, and then I want to pass in x as the temperatures again, so it fits on the same plot. And then this time I want my y to be equal to, and then we need to pass in the equation from earlier. So y is equal to our a nonlinear minus our b nonlinear divided by our temperatures plus our c nonlinear. And then I also would like to have, where's this? Okay, yeah, that's fine. So then from there, then this time, as earlier with the mode, I want it just to make sure, I want it to be, oh shoot, let me see, partly Python scatter lines. I believe it's lines, but I just want to double check. Let's check this. Okay, there we go. Okay, whatever. We will just go with mode lines. Okay, there we go. So yeah, now we can see we have a pretty decent equation, except for right here we can notice that it just goes from right here to right here and it doesn't kind of curve up, but we can go ahead and fix it later. That's just through the nature of the regression, just because we don't have enough data points from here to where it can't just guess on its own how to fit the plot like that. But we can fix that just by adding in some more temperature values, and it'll make some it'll fit the plot through those. So that's a nonlinear regression, but as I said, we're going to go through linear regression as well, because it can be done both ways, because sometimes nonlinear regression doesn't always work out for certain equations, and sometimes linear regression doesn't always work out. Now, it just so happens in this case linear and nonlinear work out for both, but we can just run through both. So if I actually go back to my iPad real quick, let me pull this up. Side, and there we go. So that was from before. So if we look at this equation now, it's nonlinear just because of the fact that this t plus c is there, so that makes it a nonlinear equation. Very non-complicated nonlinear equation, but nonlinear nonetheless. So what we can actually do is, if we take this, we can, so let me just rewrite this. If we have log minus a minus b over t plus c, we can actually multiply this t plus c off to both of these to make this log t plus c minus our a, or shoot, minus our t plus c multiplied by the a, and then this is just the b right here. So then if we factor all these out, we can do log of t plus log of c yeah, I think this should be I think we should go back to the original equation actually. So yeah, I think we definitely should. So instead of this being a minus right here, it'll just be an equals. So plus of c equals at plus ac plus b, or minus b. My apologies. Minus b. So ac minus b. So then what we actually want to do, since we are trying to find these unknowns, we're going to want to keep this log times t on this side, and then we're going to move the log times c over the other side, so it'll be at minus log of c, and then we'll have just the plus ac minus b. And for simplicity's sake, when we are setting up this equation, we are just going to be calling this d because they're all constants, so we can set another arbitrary constant d in here. So then now what we're actually going to be doing is we're going to be utilizing matrices. So when we have this, our first unknown, so we can take these and move them over here. So we have all of our temperatures right here. We can put that in one list, so T1, T2, just all of our temperatures that go all the way down. And then we have our negative logs. So the log of the vapor pressure is negative, so negative log P1, negative log P2, all the way down. And then what we're actually going to do, and it'll make sense later, is we're just going to have a list of all ones to correspond with the length of the amount of data points that we have. So we're going to make that all one matrix, and then we're going to have a separate matrix of our three unknowns. So we have A, C, and D as our three unknowns. So we have A, C, D. And then this is equal to the log P times T that we have right here. But since those are two known numbers that we have at the same time, we can just put that in one. So we have T, all of our temperatures again, and then log. So log P. And then all the way down for the amount of data points that we have. So what we can do is, if this was algebra and we could legally, according to math terms, we would be able to just divide this over by this side to find A, C, and D. But with matrices, it's extremely complicated, so we can't actually do that. So the way that we're going to want to be able to do this is we're going to take the transpose of this matrix, and so instead of doing this, we'll assign them variables. So we'll call this W, we'll call this R, and we'll call this O. So what we're going to want to do is, to be able to find R, is we're going to want to take the transpose of W first and then multiply it by every one of these. So the transpose of that. And then, so now, instead of this being a 3 by however many matrix, this should be a 3 by 3 matrix now, W should. And since this is a 3 by 1, and then this should also be a 3 by 3, or I think this might be a 3 by 2. I forget after how transposing it. So now we're getting closer to where we can actually multiply them and have it work out perfectly. But for that, even after multiplying, still we're going to be multiplying and getting a number from A, C, and D that we don't know. So what we're going to do is we're actually going to want to take the inverse of this and multiply it by that. So we're going to be multiplying this all by the transpose inverse of all these, just to get rid of this, because then the definition of this will be an identity matrix, which is just essentially zeros and ones all the way down. Ones are going to be on the diagonal, so I mean it'll be like this is an example of an identity matrix. It's ones all along the diagonal for however long the matrix is. And if we do that, so for this it would be a 3x3 identity matrix. We're just multiplying 1 by this so that we can figure out, because multiplying by 1 is just itself, so we are going to be able to figure out A, C, and D from that. Yeah, so we're gonna take the inverse of that and multiply it over here too. So the transpose of W, the inverse of the transpose of W times the transpose, everything like that, and that goes for here too, so we'll be able to figure it out. So if we code that in, all we have to do is just code in this matrix, and then all we have to do is just plug in these variables and then take the transpose of that, and it should be able to give us the correct true variables. And then from there, since we have D, we can easily solve it using algebra. So D is just equal to, or because we still need to find B, sorry. So all B is going to be equal to is just our AC minus D. So if we do that again, let me stop mirroring again. So if we do that, we are actually able to do this. So what we're going to do, so as I was saying before, so W is equal to numerical Python dot C underscore. Now what this is doing, the C underscore is a shorthand notation for a much longer line of code. What it's going to be doing is it's going to be taking all of those arrays, since arrays are essentially however many long by one matrices. So there's only one row for however long, but what we want is to have those rows shift downward. So the C underscore actually splices all of those into rows, so it just kind of flips it over. So if we do that, we can pass in all of our temperatures as one row, because we want the temperatures, and then we also want the negative of our log P. And then what we're going to do is we want the column all the ones, so numerical Python ones, and then we're actually going to use this function down here, ones like, and we can just pass in the variable T. So what that like is going to do is it's going to make a row of ones, or it's going to make an array of ones that are the same length as the array T, so that the matrix is complete. So then we have that, and I just press in W. You can see we have all of our temperatures right here, all of our negative log values, and then all of our ones. And what we can do from that is next we're going to have to take the, so if we want just the, I forget what variable I used, let me look, R, I used R. So I can do, if we want just the R, so we have to take W dot T, so, or dot capital T, we want to take the transpose and multiply it by W. So matrix multiplication in Python is with an at symbol. So we do W dot transpose times W. So then now if I shift enter that, you can see we get a 3x3 matrix now, and we're getting closer to where we can actually multiply that technically by the ABC value. But next we want to actually take the inverse of this. So if we do that, excuse me, and then we want to import numerical Python again, because the inverse function is within numerical Python within a subset category called linear algebra. So linalg dot inverse. I don't know if I did that right. I think it should have come up. Yeah, no. T dot linear algebra dot, oh, it's just INV. Okay, that is a big mistake. So now that is the inverse of our transpose. And then what we actually want to do is multiply that by the transpose again, because that's what the R value, when we did all the algebra as before, you can see that. So another at, and then do W dot T. So then if we do that, you can see that we get this, and it might seem like we're taking a step backwards, but then if we multiply again by our last matrix, which was the matrix of our regular logs times the temperatures, so we can do all of our temperatures and then times our log P. Shift enter that, and then now we get three numbers, and these are our A, C, these are our A, C, and D values. But like I said before, we want our A, B, and C values. So what we can do actually is we're going to do the same thing as before, is where we can allocate three variables at a time, because it returns three variables after the function is called. So we can call this, so the first one's A, so we can call it ALR for A linear regression, and then our C linear regression, and then our D linear regression is equal to this. So press shift enter again, and now those are our three variables, but we want our B. So we can do BLR equals our ALR multiplied by the CLR, and then subtract the D linear regression. So now we get that, and then we should get that BLR is equal to, did I press shift enter? Yeah, okay, there we go. Our BLR is equal to around 1,771. So as before, when we got all these numbers up here, we can just go ahead and plug that in, because this is now the linear regression version of this. So if I get rid of this, and I can go ahead and plot these numbers. So same thing, so figure, not plot, figure dot add scatter, and then I just do the same thing. So X is equal to our temperature values, and then our Y is equal to our A linear regression minus our B linear regression divided by our temperatures plus our C linear regression values. And then as before, I want to make this a line, so lines, and then do that, and missing a keyword argument. Okay, it's because I forgot to put in mode. That would make sense. It's not defining. So now you can see it looks like our one overlapped the other, and it almost did, but if we actually zoom in on a certain spot a bunch, we are able to see that they do not overlap each other, but they're very similar. I mean, they're off by 0.001 of a data point, which is very, very close, but they're different for various reasons that are way more complicated and would take a whole other video to explain. So now if we go back out, so we set axes. So now, as mentioned before, it's the same thing where it jumps from this point to this point, and we don't necessarily want that. So what we can do actually is we can pass in more X values or temperature values. So what we can do is we can do it down here. So if we do our tnew, let's say we'll set it as tnew, and we do numerical Python Yeah. Numerical Python dot linspace. So linspace, which will make you give it two ranges, a minimum and a maximum, and a number to a number of points that you want it to evenly distribute between those. So what we're going to pass in is numerical Python again dot minimum. So we want the minimum of our temperature values, and then next we want the maximum, not the maximum of our temperature values, and then we can say, let's say we want 1,000 points in between. So we do that. So now we have a new function called tnew, and now if we can plug that in anywhere that we have our t values. So, excuse me. So anytime that we plot, our x now we can change it to tnew, and tnew, and then up here as well on the other plot. Where did it go? Let's see. Okay, add scatter. So tnew. Oh, but I did that after. Hold on. Let's see if that still runs, even though I ran it before. So restart and run all. Just restarts and runs it in order of how I wrote it. So probably, yeah, it gave me an error here. So if I just take this and cut it, and then I'm going to put this down one and put this above. So now if runtime, restart and run all, I can go ahead and run those again, and it should work this time. Yes. And so now with the more points, you can see that we have a more curved off curve, and it doesn't just jump from one point to the other. So this is more of a fitting equation where we're going to be we can more easily predict the log of the vapor pressure, or just the vapor pressure in general, at a certain point. So let's say we wanted to find it at 375. We can look around and see, okay, it's going to be around the 5 mark, and then we can just take the e to the fifth, and figure out that that's going to be the vapor pressure at that certain point. So now it does the same thing for the other one. And again, if we zoom in, we can go ahead and see that they're still very, very, very close, but so slightly far off. But again, it would take a whole other video to explain. And then everything else with this, we can, if we wanted to label plots, we can. It's the same thing. It would just be figure dot name axes, I think, or axis title, something like that. And we can play around with this as much as we can and manipulate the plot. But for math-wise speaking, this is nonlinear and linear regression for the given data of water vapor pressure. And yeah, that is about it, I believe. So like the video and subscribe. Let me turn this off now.